In this lecture, we are going to look at a modified version of the recommenders code. This notebook will make some major improvements on the previous code, and also I will talk about how I discovered what modifications to make. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. Okay, so before we look at the code, I want to make a special note about why it was rewritten and why it might confuse a lot of beginners. So from a general software engineering perspective, everything we did in the old script was totally right. We were using the functions that PyTorch had given us, and we were doing things the PyTorch way. One thing I really advocate against is when students come to me and say, "Hey, lazy programmer, why did you write your code this way? Why aren't you using this built-in function instead of writing this complicated code that's hard for me to understand? Why are you reinventing the wheel?" And if you're a beginner, or maybe you don't have that much experience yet, but you are a newly minted software engineer who is very intent on following the rules and being a good, well-behaved software engineer, then you would tend to agree. But I hope to teach you why this is a bad idea. And I hope that you will learn that being a good, well-behaved software engineer is not always optimal. So first of all, if you're taking a course because you're trying to learn how something works, then you should expect to implement some things yourself. That's what learning is. As always, my rule goes, if you can't implement it, then you don't understand it. Okay, so maybe it's hard for you to understand, but this is not a valid reason for you to not do something. If it were easy, then you wouldn't need to take a course on how to do it in the first place. If it were easy, you should be able to figure it out yourself. So if you're looking for things to be easy, then you're probably taking the wrong approach. I'm not a fan of programmers who excel at reading documentation but are poor at problem solving. Programming isn't an exercise in memorization, but rather, it's a task that involves building and putting things together from basic building blocks. It's better to ask, how can I build this, rather than asking, how do I spell some function name that does this? One is a spelling exercise, and one is a thinking exercise. Some people say, hey, you're the lazy programmer, aren't you supposed to advocate the lazy approach? And to that I say, being lazy is good, if you're the good kind of lazy. Good lazy is when you're being more efficient. Bad lazy is when you're trying to be more efficient, but that leads to you being less effective and less skilled and less knowledgeable. So keep these ideas in mind as we go through the lecture. Okay, so in this script, since it's so similar to the previous one, I'm just going to go over the things that are different. So let's go down to where we define the model. Now, it's pretty obvious that I've trained this model many times in the past. In fact, I have an entire course on recommender systems. So I noticed that when I implemented this model, aside from the fact that it was training very slowly, it was also not getting the mean squared error I expected. So you might wonder, how do I debug something like that? If I know my TensorFlow model performs very well, but my PyTorch model does not, what can I do? Well, here's one thing you can do. First, you want to make sure that both models are equivalent. So if I create both models side by side and I copy the weights from one model to the other, I should get the same model predictions given the same inputs. If I don't, then something is wrong. So you check that, and it's a good sanity check, and let's say that it works. The next thing to ask is, well, maybe the optimizers are implemented a little differently, or they have different hyperparameters. This is totally possible. So you can test that as well. Basically, you write your own custom training loop, and for both models, look at the data at the same time and do the exact same updates. If both optimizers are the same, then both the loss per iteration and the model parameters should be the same after each update. So you can plot the loss per iteration for both models, and if they're the same, then that means the optimizers are the same. So that's a good sanity check as well. Of course, before you start the training process, you have to make sure that both models start with the exact same weights. Luckily, you already know how to copy weights from one model to the other, since that was your first sanity check. Okay, so let's say you do that and the loss per iteration is the same for both models. Now what? Well, you have to ask, are you getting the worse mean squared error or the better mean squared error? If you copy the PyTorch weights to the TensorFlow model and both the optimizers are the same, then you should see the worse mean squared error. If you copy the TensorFlow weights to the PyTorch model and both optimizers are the same, then you should see the better mean squared error. So at this point, you're narrowing down the source of the problem. Basically, it has to do with weight initialization. This is a topic that's outside the scope of this course, so if you're not familiar with it, please don't worry about it. You can learn more in my in-depth series. But basically, there are different kinds of weight initialization. For example, you might sample from a uniform distribution or a Gaussian distribution. From there, you can choose the limits on the uniform distribution or the variance of the Gaussian. Sometimes, programmers will make this dependent on the dimensionality of the input or the output. Well, long story short, if you plot a histogram of the initial weights of your PyTorch model and your TensorFlow model, you'll notice that they are not the same. In other words, that's the source of the discrepancy, is that PyTorch initializes their weights differently than TensorFlow. Luckily, we have only two different kinds of layers in our network, embeddings and dense layers. So what we have to figure out is, where are these differences coming from? How does PyTorch initialize those layers by default? And how does TensorFlow initialize those layers by default? And if they're both different, do they both matter? Or maybe it's that only one of them matters. Lucky for you, I've done all this work. So what you get after doing a little digging is that although both the linear layers and the embedding layers are initialized differently between PyTorch and TensorFlow, it's really the embedding layer that makes a huge difference. Specifically, if you check the PyTorch documentation, you'll see that PyTorch initializes the embedding matrix to come from the standard normal, regardless of the dimensionality. It's actually very surprising that this makes a huge difference, since, as you know, we like to standardize our inputs before putting them into a neural network. Well, if you sample from N01, then our inputs will be exactly standardized. So it's kind of surprising that this leads to poor results. In any case, what I ended up doing was manually initializing the embedding layers to come from a normal distribution with a standard deviation of my choice. So this is how you would do that. So for each of the embeddings, we can access the weight attribute, which then has a data attribute, which we can set simply by using the equals operation. On the right side, we create a parameter object, which wraps a tensor object, which wraps a NumPy array. And that NumPy array is a random matrix I generated myself. Alright, so that takes care of one part, which is the accuracy of the model. But we also have this problem that the model trains extremely slow. So you'll notice that in this script, there are no more data loaders or dataset objects. So we just go straight to the training function, which takes in two new inputs, the train data and the test data. These are just tuples that store the NumPy array versions of the data. And if you've taken my in-depth deep learning courses, then you're in luck, because we've written this loop many times for ANNs, CNNs, RNNs, and so forth. And back in the old days, you would actually have to write this kind of thing yourself. And by the old days, I really mean like 2 or 3 years ago. So don't think what I'm doing is some kind of ancient secret or something. This is still in the deep learning era. Okay, so basically we're going to iterate through the batches manually. Now most of this is the same, but some of it is a little different, so I'll walk you through the different parts. And by the way, if you already have some idea of how you would do this yourself, you should try to do that before looking at this. So one thing that we need to do is calculate how long the inner loop will even be. It's going to be the number of batches. But how many batches do we have? Well, that's roughly the number of samples divided by the batch size. Of course, they may not divide evenly, so we need to take the ceiling and then cast the result to an integer. So inside the main training loop, we first shuffle the data. We do this on every iteration to avoid unwanted correlations. Then we do our inner loop through each batch. Inside the loop, we grab the current batch. The index range is j times batch size up to j plus 1 times batch size. You want to verify this for yourself by writing it out on paper. Next, we convert the batch to tensors and move the data to the GPU. Then we do our usual gradient descent step. And down below, we do a similar loop over the test set, since this also may be too large to fit into memory. You should confirm that for yourself. Okay, so next we call our training function after splitting up the data. This is almost the same as what we did earlier, except that this is in pure NumPy, and we only need to convert to tensor when we're inside the training function. Alright, so here are the results. So if we look at the output from our training function, we notice two things. First, the accuracy is much better. These results are on par with what you would get with TensorFlow. But note that TensorFlow works right out of the box, whereas you had to do some customization in PyTorch to achieve the same results. Second, we noticed that the duration per epoch is much lower than before. Before, it took over 5 minutes per epoch, and this takes just under 1 minute per epoch. So that's over a 5x speedup, just from writing our own training loop and not using the built-in datasets or data loaders, which is very interesting. So let that be a lesson to you. Don't blindly take the approach of everyone must use libraries in order to be a proper software engineer and don't reinvent the wheel. Most people who say these kinds of things do so because they can't code. And because they can't code, they don't want anyone else acting like they can code. They want everyone else to be just like them to appear that they have the same skill level. So don't be like these people. Instead, know how to implement things yourself. Know how to investigate and debug and things like that. Otherwise, you'll just be a slave to APIs and libraries.